There is more research on vortex generators than you can poke a stick at, but most of that research is for very subsonic flows, and for subsonic flows, we understand how they work pretty well. But what about when you put a vortex generator in supersonic flows? How do they behave? And would you even want to put them in supersonic flows? What are their benefits? How would their vortices affect the shock waves? That is what we're looking at today, and to do so, we're looking at this paper called Numerical Discovery and Experimental Confirmation of Vortex Ring Generation by Micro-Vortex Generators. Now, this paper is open access and you can find it in the link below, but for the people at Elsevier, I don't know exactly what the Creative Commons license is, because if you go to the Creative Commons license here, it just opens up a generic page with a bunch of different ones, and I don't know which one is applicable to this paper. Considering that it's online for free and you can just access it like that, I'm guessing it's okay to do this podcast on. Anyway, let's get into this paper. So the researchers looked at micro-vortex generators and how they affected the shockwave boundary layer interaction and just the shockwaves in general. And the results they find are really cool. Now, as a general rule, a micro-vortex generator is one where the height is about 1/3 of the boundary layer or smaller. And in regular subsonic flows where there are no shocks, micro-vortex generators are used when you want to get the benefits of regular vortex generators, like delaying stall, but you don't want the drag that the regular vortex generators would produce. As such, by making them so short, the vortices that they create are then smaller and then they stick in the boundary layer much more. So you don't get the drag penalty from the actual object itself plus the vortices. And you would still get some benefits, and often if you design them well, all the benefits without any of the downsides. Now that is for subsonic flows. What about supersonic flows though? Let's find out. So in figure 1, you can see the micro-vortex generators these researchers tested. They are the simple and very common ramp ones. And they are commonly used throughout aerodynamics because they do a pretty good job and they're also very simple. They are literally just a triangular prism with a chamfered front. So the flow comes in from left to right here, and then it just spirals up into vortices. And these ones create pairs of counter-rotating vortices. One vortex on one side rolls up and the other one on the other side rolls up in the opposite sign. So counter-rotating vortices tend to be better at mixing higher momentum fluid from higher up in the boundary layer into the lower region of the boundary layer than co-rotating vortices do. And these researchers tested this particular micro VG at Mach 2.5, so very subsonic, and shocks should form off of this bad boy. Now in figure 2, we see the geometry that this micro VG was integrated into. It is just the head of a ramp, so the flow comes in here, hits it, and then goes up this ramp. And one thing that we should keep in mind is that these researchers say that this micro VG had a height between about 30% and 100% of the boundary layer that would form in an incompressible flow. Not compressible, but incompressible. So this ratio of 30 to 100%, what is it in the compressible flow? We don't really know. They don't mention it here explicitly. So in reality, this micro VG may actually be a regular VG in reality and not micro. That's just something to keep in mind as a general note. Now, to test this VG in a Mach 2.5 flow, they used CFD. And at this speed, the Reynolds number was 5,760, which is really low. And they did LES on it, which is really impressive considering the velocity of the flow. Now, one thing that is quite novel about their LES approach is that they didn't use a subgrid scale model like the popular Smagorinsky scale. They said that the LES approach they used is called implicitly implemented LES, which means that instead of using a subgrid scale to find the energy of the smaller vortices in the flow, they actually used what they say the intrinsic dissipation of the numerical method to dissipate the turbulent energy accumulated at the unresolved scales with high wave numbers. So what does that mean? Well, first of all, let's quickly recap what LES means. So LES stands for Large Eddy Simulation, and the core idea behind this approach is that you resolve the larger vortices in the flow, with the assumption being that these larger vortices contain most of the energy, at least the turbulent energy, in the flow. Then for the smaller vortices, which still have some energy, but by comparison not very much, you use a subgrid scale model, like the Smagorinsky scale, to approximate how much energy these smaller vortices have in the flow. That is the typical LES way. Now, the authors here didn't use this exact approach. They did resolve the larger vortices, but when it came time to resolve the smaller vortices and the turbulent kinetic energy these smaller vortices have, from their description, the LES equations used have their own inbuilt variables that model this energy. So it will be particularly interesting to see how this CFD approach fares compared to other LES approaches. And for their boundary layer, now the fun starts because they have to consider the temperature effects, which for regular incompressible flows you usually don't have. So the wall, and I'm guessing the VG2, is set to adiabatic, so this surface here. That means that no heat transfer is going to or from the wall, and that then takes out the variable of the wall's material, so for example the heat transfer rates and the thickness of the wall, etc. And they also have a no-slip condition for the wall, which is good because without that you wouldn't get the boundary layer forming, and hence the vortex generator wouldn't be doing what it's supposed to. Like, how would you create these vortices to mix in momentum in the boundary layer when there's no boundary layer to begin with? Now for the left and right walls, they set them to periodic boundary conditions, so this wall and the one on the outside. And that means that they are pseudo-simulating many vortex generators right next to each other. However, as the authors acknowledge, that potentially alters the results because if there is an asymmetric flow over a vortex generator, then multiple VGs next to each other won't pick that up and you just get a symmetric flow. So that's potentially some sort of inaccuracy there. But for one regular vortex generator, it's completely fine. But because they are now doing LES, it is also very understandable that why they could only simulate one VG, and they had to use this periodic boundary condition to simulate the entire VG array. And something that is really cool is that they calculated the temperature at the wall of the inlet flow with the first equation here in 2b. So with this equation right there, this tells us if we know what the temperature at the wall edge of the boundary layer is, so TE is, and the back number is, then you can calculate what the wall temperature will be. And then you can then use this second equation to then calculate what the temperature profile is through the boundary layer. And this is also a big deal for compressible flows because compressible flows do come with temperature fluctuations, whereas incompressible flows, if you don't have any temperature heat transfer, then you don't need to worry about that. So these are two cool equations which you can figure out what the temperature through a boundary layer is based on the Mach number and the temperature at the edge of the boundary layer. Now in figure 3, we see the boundary layer profile of the inlet flow. And overall, the important thing to take away from this is that the authors say it represents a boundary layer that is growing turbulent through natural means instead of going through a very sudden transition like bypass transition. In other words, the turbulence is growing steadily and will break down relatively slowly. Now, that is almost all the CFD information that we have. The only other real important piece of information that they give us is that they used 40 million cells for their setup. Now, there's quite a lot, especially given how small this object is, and the domain in general, I mean, it's just a one vortex generator. But that's the thing with LES. You need to use such a fine mesh to capture the structures with most of the energy. So you have to use a lot of cells and have a very fine grid. And coupling that with the fact that they're using Mach 2.5 for the flow, that makes things even harder because you have to have an even finer mesh now to pick up all the important turbulence. So imagine how many cells you need to use if you had DNS. So that kind of leaves us with no mesh independent study or validation. And in fact, actually the validation data is an interesting one because they do give experimental data to confirm some findings they get in the CFD later in the paper. And once I read the paper, I saw that, but they wait until much later to give this data. So the CFD is kind of validated, but not here yet, and they don't go through it explicitly. So the mesh independent study may have not taken place because the authors don't have the computational resources to do it. Again, 40 million cells for one VG is quite a lot. And if they needed to use 80 or whatever, maybe they didn't have the computational resources to do it. So that's understandable. But the CFD is at least partially validated, as we'll see later on. So factoring all that in, the CFD might be around about a 7 out of 10, and the trends and general flow features have been validated. And just as a quick side note, if you want to learn how to do OpenFOAM, which is a really good and free CFD software, but hard to learn, then take our course at the link below. So let's move on to the results now. Now in figure 6, let's scroll down to that one, we see the isosurfaces of the CFD in the top two figures, and it is really interesting because we see a vortex ring, or at least half a vortex ring, you can see here zooming in, that then joins the ground. So the vortex generator isn't producing two vortices, one on each side of the opposite sign, but a vortex ring that if you were to just take a snapshot on each side, you'd see a vortex of the opposite sign, but in fact, that vortex you'd see just belongs to the bigger vortex ring structure. And it's all just one big loop. As such, the next finding is very understandable in that the authors say that the Kelvin-Helmholtz instability is what is causing this vortex loop to form. Now, the Kelvin-Helmholtz instability is where you have two layers of fluid flowing over each other, and at the interface, you obviously have one flow moving faster than the other. That causes vortices to form at that interface, and it is really cool, and the authors are saying here that this vortex loop is forming because a shear layer is forming over the vortex generator. In other words, there are at least two flows of different vortices going over each other, and that creates the shear layer. And the shear layer then produces this vortex loop through the Kelvin-Helmholtz instability. And I really wonder how the shocks, if any, that are coming off this VG are affecting the shear layer. I don't know. Let's see later if they give information on that. Now in figure 7, we see the flow over a vortex generator in several cut planes. And we can clearly see two shocks forming, one here and one here. And interestingly, one shock forms at the start of the vortex generator. Down here, you can't really see it's out of picture, but it's about where that should coincide if we chase it back. And the second vortex generator forms at the end of, the second shock forms at the end of the VG. So that tells us that either the flow past the first shock is either still supersonic and then creates a second shock, or the flow accelerates and forms a second shock, or the second shock is effectively an expansion shock. But anyway, from this figure, we can clearly see the vortex rings forming in these little blue circles. And they appear as circles because the plane is cutting through this ring. These circles are actually part of this entire ring structure going from left to right and going down to the ground. So the authors say that pretty much anything that isn't orange or red indicates a momentum deficit. So probably a flow of a different speed here. So this blue and green and yellow region. And we can clearly see that these blue circles, so the vortex rings, form at the interface between the orange flow and the green flow, hence a shear layer. As such, in this CFD, the Kelvin-Helmholtz instability definitely seems to be the driving mechanism in this vortex ring creation. And in figure 8, we can see a really clear image of the turbulence over the vortex generator, and also we can clearly see two shocks forming, one here and one here, and again coinciding with the start of the VG. And between the two shocks, there definitely seems to be some turbulence that is trying to organize itself into coherent vortices, but isn't quite able to do so yet, it seems. But then past the second shock, we see the vortices forming quite clearly. You can see them rolling up very nicely. And now in figure 9, we see some experimental data of this exact setup. The top image is for PIV results, and the bottom is for the acetone vapor technique. Now the second image for the second technique from the author's description is they used the PIV laser to quickly illuminate the flow, and the vapor appears as white because it reflects the light. And the vapor picture is really nice and clear, like this is phenomenally good quality. You can see everything really. For a supersonic flow, this is really good. And both of these pictures show the exact same phenomenon of the vortex rings forming, and the location of formation seems to be at the shear layer as well, thereby confirming the Kelvin-Helmholtz instability mechanism proposed by the authors. Okay, so now we know that this vortex generator creates a vortex ring, and the underlying mechanism is this Kelvin-Helmholtz instability, but does it affect the shocks at all? Well, in figure 13, we see the CFD results of how the vortex ring interacts with the various shocks in the system, and as it goes through time. Now, interestingly, these figures show that the vortex rings first approach the lambda foot of the shock forming, so this front part here, this front gray sheet. And if you don't know what a lambda foot is, check out our YouTube video called Lambda Shockwaves, the Weirdest Shockwaves, Aero Fundamentals number 51. In that video, I go through what a lambda shock is and why it forms. So anyway, back to this research. So the vortex ring enters the front foot, and then the shock exhibits an instability that then travels up the shock wave, and it continually gets bigger and bigger, I guess. So the vortex ring effectively punctures the front foot of the lambda shock, and that shock breaks down. That's really what you can see in the subsequent pictures, that this front foot breaks down very quickly. And then the vortex ring hits the rear lambda foot as well. Now I can't quite tell if the rear foot also disintegrates or not because there aren't any more pictures in this time sequence. But even still, the vortex ring breaking the front foot is a boss move, and it also leads to the collapse of the separation bubble between the two lambda shocks, the two lambda feet. And then again affects the shock wave going up. So what happens to the vortex ring, and is it weakened? I can't quite tell from this data, but the fact that it is passing through such a great change of pressure, i.e. the shocks, makes me think that it probably would be breaking down too by this point. But at the very least, we can see that the vortex rings greatly manipulate the shock waves, and in beneficial ways too. It can literally get rid of some shocks and alter the pattern of another shock and simplify the flow even. And with that, we come to the end of this podcast. I really liked, especially the ending, which I wasn't expecting such a big effect from the vortex rings, because they're generally weaker than the shocks. But on the other hand, shocks are very sensitive to disturbances. So I guess the vortex rings won the fight because of that. And with that, if you want to learn OpenFOAM or get better at CFD, take our course in the link below. And if you're doing experiments, did you know that there's probably a 2 to 4% error in your data and you don't even know about it? In the Atmosphere Hawk link below, we go through the math as to why and how to fix it. And with that, if you like this podcast, hit the like button. And if you want to see more like this, hit the subscribe or follow button, whichever platform you're on. And we'll see you one. Peace, amigos.